Hello, and welcome back to Unit 6 on circular motion and universal gravitation. In Part 2, we're going to do some examples of uniform circular motion. The first one is involving a ball rotating on a string in a vertical circle. We're given the mass of the ball at 0.3 kilograms, the radius of the string at 0.5 meters, and the speed of rotation at 4 meters per second. We want to know the tension in the string when the ball is at the top and bottom of its path. So to begin with, I'm going to draw a picture. Here is the circular path. Here is the ball at the top of the path. Here is the ball at the bottom of the path. If we think about the top, then there are two forces on the ball at the top. There is gravity pulling downward, and there is the tension in the string pulling downward. Since it is moving in a circle at constant speed, then the net force becomes the centripetal force and equals mv squared over r. And just as I've been able to do in the past, I'm going to rewrite the net force in terms of the forces acting on the ball. Since all my forces are downward, for this part, I'm going to, that is an A, which is true, but I wanted a positive sign. I'm going to define down as positive, the direction of the acceleration as positive. So I add my two forces together. I can now solve for the tension equals the centripetal force, the net force, mv squared over r, plus the force due to gravity, which is mg, minus mg, which will equal 0.3 kilograms times 4 meters per second squared divided by 0.5 meters minus 0.3 kilograms times 9.8, running out of room, meters per second squared. And that all works out to be 6.7 newtons. If we think about the bottom now, same two forces, gravity still points downward, but the string is now pointing upward. So as before, I'm going to take F net, write it in terms of my two forces. And since my acceleration is upward, in this case, I'm going to let up be my positive direction. So that'll be TSB minus WEB equals mv squared over r. Or in other words, TSB equals mv squared over r plus mg. And if I plug in the exact same numbers I did above, but with a plus sign instead of a minus sign, I find that the tension here has to be 12.54 newtons. Now, if you think about spinning a ball, just twirling something in a vertical circle, you can feel the tension changing. And the tension's having to change because you need a different tension at different points in the motion to accomplish the uniform circular motion. Next question I want to ask is, why are the curves on racetracks banked? So let's begin by considering a flat track and thinking about a top view. So here is my circular track. Looking at it from the top, I have a car going around, and I know that in order to do this, the net force and the acceleration have to point inward. If I look at the car from the side and think about the forces on it, or I guess instead of side view, you might want to think about it as the front view, but I'm looking at it from this angle. You would have a normal from the track on the car's weight, and then in order to get it to turn in the circle, you need friction. And this frictional force is gained by turning the car's wheels. Okay. But it also means that you are completely reliant on friction to be able to go around this track. So if this were slick, you would slide right off. You would not be able to make your turn. If we think about a banked track, the top view looks exactly the same. You have your circular track, you have your car on the circular track, acceleration, and now if I look at what I called a side view, but probably should be called a front view, the track is now slanted. You want to slant the track appropriately so that when you look at it, there is a component of the normal force that points towards the center of the circle, which means that without any friction, you are able to go around this circle successfully. Okay, so why are curves or racetracks banked? In order to allow the cars to go around the track more quickly. There's an additional force that will help them do this. Okay. Now you may be thinking, well, what about friction? Isn't there friction on that car on the bank track? Yes, there is friction on the car on the bank track there. But that gets a little subtle. And let's look at that when we consider the next example. So for the next example, we have an engineer wanting to design a banked circular track so that cars can travel around at a speed v. How does the speed you travel around the bank track change depending on friction? Okay. So pulling in what we were just doing, let's consider the frictionless case. So here's my bank track. There's an angle theta. Here is the normal force on the car, which I'm just going to represent by a circle at this point, and the gravitational force pointing downward. Okay. Since acceleration points to the right, I'm going to use a coordinate system which has an axis pointing to the right. So positive y and positive x like this. And that is really annoying me. So, okay. We now need to define the normal force, the direction of the normal force in terms of this angle theta. And with a little bit of effort, you can find that this is the angle theta. Okay. So now, if I look at my normal force, and I guess I should put my subscripts on, I have a triangle that looks like this. Here's my angle theta. Here's my normal force on the hypotenuse. The x component is on the side opposite, and the y component is on the side adjacent. If I look vertical, there's no acceleration in that direction. So the net force in the y direction is 0. That tells me that the normal force in the y direction minus the weight, has to equal 0, which allows me to solve for the normal force. And I lost a C there. There we go. In terms of the weight and the angle of the track. This normal force will be true for all considerations of this track, regardless of how the friction is, because the friction is going to be always in a direction No, I take that back. Nix that. This normal force will not stay the same. Okay, moving on. In the x direction, we have F net x equals ma, but it's moving in a circle at constant speed. So net force takes on the centripetal form. We only have one force in the x direction, and that is the x component of the normal force. And I'm going to apologize here really quick because I realized that I started with a T and I changed it to an R. So I started with track and then went to road. So my apologies for not being consistent with my subscripts. Okay, now that everything is in R, I have mg sine theta. No, not mg. Take 2. nrc sine theta, sorry, equals mv squared over r. I can plug in my value for nrc, which is mg over cosine of theta times sine theta equals mv squared over r. M's cancel, and I have a formula, which I'm going to write over here because I'm kind of out of space over there, for the ideal banking angle for a track. The tangent of the banking angle is going to be the velocity squared times the radius, or divided by the radius, and the acceleration due to gravity. Okay, so this is the ideal banking angle, the one that does not require you to have any friction to help you go around that curve. Okay, so let me just rephrase that one more time. If I approach a banked curve at a particular angle at the correct speed, I can go around it just fine. If I do not choose the correct velocity for that particular banking angle, I won't go around in a circle perfectly. I will move up or down the track. Okay, so now let's consider friction. And let's consider friction in 2 different ways. The first way I want to consider friction is to let the friction point up the track. Okay. So now I have 2 triangles I need to work with. The angle theta, this is theta here, this is theta again for there, and then this is theta as well, but between the surface of the track and negative x. Okay. So my 2 triangles in this case look like this. Okay, not too bad. And notice that friction equals mu nRC. Okay, we've set it, but we got components going, and I want to make sure that we're all on the same page here. Okay, if we think about the y direction, there's no acceleration in the y direction. There are 3 forces. There are 2 that point upward, the y component of the normal force, the y component of the frictional force, and one that points downward, and that's gravity. So that is nRC cosine of theta plus FRC sine theta, it's on the side opposite, minus mg equals 0. I can then solve for my normal force. Okay. If I look at the x direction, then I have two pieces in the x direction. I have the normal force pointing in the direction of the acceleration, and with friction defined this way, it is pointing the opposite direction. And that does not equal 0. Should not equal 0. Forgive, I got overly happy with my zeros there. It's accelerating in the x direction. Otherwise, it's not going to go around this curve, right? So this is nRC sine theta minus mu nRC cosine theta equals mv squared over r. So nRC equals mv squared over r times 1 over sine theta minus mu cosine theta. And all of that is in that denominator. And now I can plug in my value for nRC from above. So I think I've done math that I really didn't need to, but that's okay. mg over cosine theta plus mu sine theta equals mv squared over r times, 1 over sine theta minus mu cosine theta. So in this case, we're not going to get down to one pretty answer like tangent theta equals. It's just not going to happen. Instead, what we're going to end up with is that in this case, we get a ratio, sine theta minus mu cosine theta over cosine theta plus mu sine theta equals that same relationship, v squared over rg. And you can see if friction goes to 0, that would be a coefficient of friction mu equal to 0. Then you return to the form that we had previously, where sine theta divided by cosine theta equaled v squared over rg. Okay. Now, in this case, friction points up the ramp. What would cause friction to point up the ramp? Well, in this case, we're not turning the wheels. Okay, we're not turning the wheels, which means that naturally the car would want to slide down. So the friction points opposite that motion. Okay, if we were to point the wheels, or if we were to turn the wheels, then a couple of changes would happen. And I am going to sketch them in really, really quick for you here. If you turn the wheels, the free body diagram changes. And I will do this in a different color so that it's easy to see the changes that I'm going to make. All right. You still have the normal force pointing the exact same direction. You still have weight pointing downward. If you turn the wheels, now you have a component of friction that also points down the ramp, which is good. Now you have two forces that are going to help you turn the corner. If you look because friction changed direction, that means that the y component now points negative and the x component now points in the same direction as the component of the normal force. So that gives us two sign changes. It makes a sign change here, which results in that being different. It also makes a sign change here. Okay. So I'm very carefully putting all these sign changes in. Okay. Okay. So I'm going to come over here. This was the up the ramp version, friction pointing up the ramp. There is also the friction pointing down the ramp version. To get the down the ramp version, just change the signs. Okay. So now the question is, how can I go around this curve as quickly as possible? Okay. And to answer that question, I created an Excel spreadsheet. That Excel spreadsheet is available on Brightspace. I will put it up there for you, but I will open it up here as well. Okay. So you can see I have a couple of columns here. So the first thing I do is I define some angles in degrees, and then I change them to radians because remember, Excel doesn't like degrees. It just doesn't. I define a radius of 250 meters and a coefficient of friction of 0.5, which is reasonable for rubber on dry pavement from the table we had in the last unit. I then define the tangent of the angle, the sine of the angle, and the cosine of the angle. I also find those pieces that go into calculating the friction up, friction down. So here's sine angle minus mu cosine angle, and cosine angle plus mu sine angle. All of these are related with friction going up. Same thing for friction going down. I also take the ratio of those two, and then I calculate the velocity. How quickly could I go around this curve at each speed? So for ideal, I get 0. If there's no angle, then it's going to be really hard to go around a curve, just saying. And it goes up from there. For friction going up, I have a bunch of ones here that don't work. Okay, why don't they work? Well, there's a square root. Remember, it's v squared over rg. There's a square root to find the velocity. And it turns out that sine angle minus mu cosine angle is negative, and you can't take the square root of a negative number, which means when friction's going up the ramp, there are certain speeds for certain angles you can't go around the curve. Okay. On the other hand, when friction's going down the ramp, no matter the angle of the ramp, I get a speed, which is really nice. And then I made a graph, and I have that graph on the next slide here. So we have velocity on the vertical axis, the banking angle on the horizontal axis. You can see the bottom one. This is where friction pointed up the ramp. There was a bunch of angles where it didn't work. And then all of a sudden it started picking up. Okay. But always when friction's going up the ramp, you have to go around more slowly than the ideal speed. The ideal speed is the middle line here. And then the black is for friction going down the ramp, and that allows you to go around even more quickly. This concludes this part.